Hello and welcome to Easy Projects. So I have a project coming up where I will be using some fairly long signal wires to send a data signal back and forth. So I thought it would be interesting to take a look at transmission lines and signal reflections. So we will not go into the math and the calculations of it, but we will make a few demonstrations and hopefully we can get an idea about what a transmission line is, what a signal reflection is, and practically how to get rid of it. And then if you want to study it further, you can go look up the math and try to do some calculations, but we will not do it here. So I think we should just start by a demonstration. So I set up this microcontroller to generate a square wave, just toggling an I/O pin as fast as possible. The actual frequency of the signal is not so important, it's more that it has a fast rising and falling edge to be able to see this phenomenon. I would like to mention, if you want to measure something like this, you should use no ground lead for the probe. Just use the bare metal connection on the probe, because you'll get a much more representative reading of what's actually going on. So if I were to hook up my ground lead and my hook, you can see that already we have a big problem here, because we get ringing on the signal, which we don't really want. This is not, you saw before, this is not the actual signal that's present on the pin, but because we add this big loop and long leads here, we get a problem kind of similar to what we're going to look at. You can also use a small spring clip like this, it'll be fine also. I soldered two component leads to the board here, and I can just jam the probe in between, and that gives the best reading for me. So what do you think would happen if we take a length of wire here? We need one for the ground and one for the positive. We just hook it up to these two pins, and the other end is just open. There's nothing connected. So you can see not much happened, but we do get a little bit of ringing here. Let's continue, add one more piece. So you can see we get a bit more ringing. So I'll double the length of wire again. And you can see we get more of this ringing, but now it actually doesn't look like ringing anymore. It starts to get a bit square. Almost like a staircase that's getting smaller and smaller. And if I connect up even more wire, you'll see the amplitude didn't get much worse, but there's a longer distance between these oscillations. So to understand this, it helps to think of the electricity as a wave instead of just like a voltage. You know this from anything else, like water or sound. If you go inside a city and it's quiet at night and you like clap your hands really hard, you will hear echoes from all over the place maybe. You know that light has a speed, so it takes a certain time for the light from the sun to hit the earth, and so on, but everything has like a speed. And the speed of electricity is, you could argue it's the speed of light also, but once it's traveling inside a wire, it gets slowed down a bit, so it's not quite the speed of light. But nevertheless, it still has a speed. So if you say you apply a voltage, just a normal DC voltage at the end of the wire, it doesn't appear immediately at the other end of the wire. But if you just hook up, say, a 9-volt battery, and you have a multimeter at the other end of the wire, in theory, after some time you will measure just 9 volts there and you'll think everything is fine. But we have to know that this voltage, it starts here and it travels down the line, and once it hits the other end we can measure it. But what happens if we disconnect the battery again before the voltage reaches the far end? Well, the thing that we have sent away already doesn't know that we disconnect the battery, so this will just continue to travel down the line. And you can now see that there would be a wave on the copper, just a voltage traveling down the line, and at some point it would hit the other end. But since this requires energy, if there's a changing voltage, there must be some kind of current energy in this. So due to the conservation of energy, it can't just disappear, go out into nothing. And if the other end of the line is open, there's only one thing left actually, and that is for the signal to reflect off the other end of the cable and come back. So we would see the signal come back. And if this end is open circuit, also if you disconnected the battery, it would in theory just bounce back and forth, and of course there's losses in the cable, and eventually it will die down. So that is in fact what we see here, that the longer we make the cable, the longer time it takes for this kink here to appear. And this is in fact the reflected signal that's coming back that makes this kink in the waveform. And you can see that we have multiple reflections, and one is a bit less than the first one, so it kinda dissipates the energy. So let me just change this to a normal wire that doesn't have all these junctions here, because that will be a problem later. This wire is a bit longer even, so we will see longer time between the reflections. So this is just a normal 2-conductor wire, and used for many things like speakers or power cords or whatever. You can see just by hooking up this wire with nothing at the other end, we get this really bad looking waveform here from the reflections. So this here is actually not the worst part of the story. This is just what we have at the transmitter end. So what would happen at the receiver end, so the other end of the cable. Now I am touching this with my fingers, so it will not be exactly what is going on, but it's very close. And you can see it looks completely useless. So this is a 3.3 volt microcontroller, so the pulse that it sends out has an amplitude of 3.3 volts. But you can see on the waveform we are all the way up at 6 volts here, and we are negative 2 volts at the negative going peaks here. And our original waveform is completely lost here, and you couldn't really, like, there's one tiny little spot here in this line at around just 2 volts where you could maybe pick up the signal, but it's completely unreliable and useless. So this wire here is 2.6 meters long, and already here we couldn't send a 6 megahertz data signal through it. But surely there's something we can do about this, because if you know your normal Ethernet cable, like a 100 megabit connection can easily work up to 100 meters, and this is just 6 megahertz over 2.6 meters. So far we have used this cable with nothing connected at the other end, and that would be a typical scenario for a receiver to have a very, very high input impedance, and just measuring the voltage across the two wires, like if you use a multimeter. But what we can do is put a load across here, just a resistor, and this load we would call a termination resistor. And so you might ask, which resistor do we use? And actually there's only one thing that determines that, and that's the cable. If you have played with chargers or solar panels or something like that, you will know that to get the maximum amount of energy out of the system, you will have a load that is equal to the source impedance. In other words, to get the most power out of your solar panel, you will adjust the charge current to the battery according to the source impedance of the panel, and you can just measure that. You measure the voltage and you measure the current, and you just find the peak where those two multiplied together gives the maximum power. and that would be a maximum power point tracker. It turns out that the same analogy works for a transmission line, because we just want to take all the energy out of the line when it receives the other end. So the next question is, what's the impedance of this line? And this impedance we also call the characteristic impedance. The funny thing about that is, if it's a completely uniform transmission line, which never happens in the real world, but theoretically, if we have a completely uniform conductor and the surroundings are completely uniform all the way along the cable, it doesn't really matter how long this cable is, it will have the same characteristic impedance. And for the transmitter, it will look like an infinitely long transmission line if it's terminated with the right load at the end here. And we'll get no reflections because all the power will be dissipated in the load. So we don't really know about this wire. We could roughly calculate the characteristic impedance of this. I don't actually know what it is, just a random wire. I think I cut it off some lights or something. But the manufacturing tolerances wouldn't make it very reliable. But you can buy cables like coax cables or coaxial cables that is manufactured to a specific characteristic impedance, and most of the time you'll find this written on the cable, like here, 50 ohms for this one, and you can get coax in different impedances, like 50 ohm or 75 ohm is very common. It doesn't mean that there's any resistance in the cable, that it's not 50 ohm from one end to the other. So this determines the termination load that you should put on the other end of the cable to get no reflections through it. So you might have guessed it already, we can very easily find the characteristic impedance of this wire by connecting a variable resistor here, a potentiometer across it, and then measuring the transmitter, and see when we get no reflections on the signal, we know that we found the right termination resistance, which will be equal to the characteristic impedance of the cable. So let's try that. So I just soldered a 5 kilo potentiometer to the end of the cable, and this now has 5 kilo ohms termination. This is far too high, and if we measure it at the transmitter, we see that it had pretty much no effect on the signal. But if we start turning this, you can see at some point it starts to get better. Oh, too much. And right around here. Maybe you also noticed if we go too far, we get the opposite effect. Before we looked at if the signal was open, we get a positive returning reflection. If the output was shorted together, we would get a fully negative reflection coming back. I don't want to short this really, because it's just the output pin of the microcontroller, and you can see that the amplitude gets much worse also when we will put unnecessary load on there, so let's not do that. But now we found the characteristic impedance of the line, and we can actually just go and measure it. So what we get here is around about 125 ohm. So that means if I want to send my signal down through this wire, I will add a 125 ohm termination resistor at the receiver, and then both ends of the signal should look perfectly fine. This is not a good cable for any high frequency communication at all, and you should really use a cable that's made for it, like a Cat5 Ethernet cable or something like that. And for that cable you will also get the characteristic impedance specified by the manufacturer, so you don't have to guess it. So just for completion, here we see at the transmitter end, and for good measure we give it a try here at the receiving end. You can see it's not as nice, but it's pretty good. So there is another thing that I would like to demonstrate also. Remember I said that this transmission line has to have a uniform characteristic impedance, and that means that, roughly speaking, that it has to be one cable without any connections, and it cannot be damaged in any way, and it should have the same shape. Like if I were to open this cable like this and change the impedance here, you can see we get a reflection. So this is at the far end of the cable, and I want you to notice the precision of this. So let me put it in the center of the screen there. So if we put this back as best as we can to normal, and I go roughly to the middle of the cable and I open it, just break the two wires apart, you can see that the reflection happens sooner. Before it was here, and now it's here. And now you can see I've kind of permanently made this transmission line worse than it was. And that's why, again, a coaxial cable is the preferred method, because it has one conductor wrapped around the other, and it has a fixed distance from the outside of the shield, which is one connector, to the core inside, which is the second connector. And this can be precisely manufactured, and the outside forces that act on this doesn't really change that property. But if you were to bend it really sharply so it gets a kink in the wire, or you hit it with a hammer or something, so you change the physical dimension of the cable, it will be no good anymore, and it will start to make reflections. I'm not exactly sure how much a tiny little defect would have, but it will make a difference. Of course, it wouldn't be any good if you couldn't make connections between cables and send signals long distances. And in fact, this can be done if you control the impedance of the connector also. So in a 50 ohm BNC, for example, they will try to match this impedance of the connector to 50 ohm also. So there's a lot more to this, and I guess I could be rambling on, but also I'm not an expert in this at all. I just know the very basic things. But one common thing is that if you also want to get rid of these defects, you can put a termination at the source also, so a series termination, so if anything gets reflected back, it will also be eaten up by this resistor at the source. So I hope you liked this video. It was just a relatively quick and practical demonstration of why this matters, showing that even for a relatively complex topic you don't really need to do any math if you just want to do a bit of groundwork. So a project that I hope to be starting on soon will include an Arduino and some sensors, a keypad and some sirens, and maybe some flashing lights, and maybe a smoke generator. Who knows? I'm not sure this will be necessary to think about, but it's always a good thing to think about it, because the data rate in that project probably will be very low. But again, the voltage spikes that you saw at the far end of the cable with no termination, that could damage the equipment. So that's one thing to think about also. To solve that, we could also increase the rise time a lot, so that it's a lot more than the time it takes for the signal to reach the end of the cable. and then this effect will pretty much go away also, but that will limit the data rate a lot. So again, thanks for watching, and please subscribe to the channel if you want to see more, and I hope to catch you soon for the next video. See ya!